All right. They told me it'd be a big crowd today. This is a pretty good sized crowd. This is about the size of my average freshman class, so we can take it from there. Now, as Brittany told you, my name is Danny Taylor, and I have been asked to come over and talk to you folks about engineering and how I got to where I am, what I do, what my research consists of, that sort of thing, so that you'll understand maybe a little bit about engineering. So I am an engineer, but I'm not just an ordinary engineer. I happen to be a mining engineer. Scary, what's a mining? And I knew I had to say that to you this afternoon, and you've been listening over the last 3 or 4 weeks to some very impressive people who have come in and talked about the work that they do as primarily scientists. And from what I understand, their work has been highly relevant. I mean, you heard about from the guy from DRI who studied the ice cores, and so he's mapping climate change. There may be only 1 or 2 things in the entire world that is more important than understanding climate change. So highly relevant. You've heard from a woman from the biology department about internal organs and things like that. Boy, that sounded like a cool one. But certainly, understanding how the human body works is critical to our understanding of health and medicine and making sure that all of us have healthy, long, productive lives that we can enjoy. Scott Menzie from Geography came in and talked about the work that he's doing with pollen. Now that sounds like a pretty dry subject to start with, but really I'm sure that Scott connected that to things like climate change, because that's very important. So you've heard from some people with some very relevant disciplines and very relevant information to share with you as you're looking out there trying to find what do you want to do, and perhaps something involving science, technology, engineering, and math. So what in the world is someone who is a mining engineer coming in here and trying to convince you that what he does for a living is as relevant, maybe more so, than the other things you've already heard about? Now that sounds like a pretty egotistical statement for me to make. But I've got some people to back it up over there. I've got my students who stand behind me on this. Let me just throw this out before we get started, because I want you to be thinking about what I'm talking about today, that is the field of mining and all the stuff that's involved in there, with some context. Because most people, when I talk to them, and it doesn't matter whether I'm talking to people who are in high school or people who have been out of school for 20, 30, 40, 50 years, most of them have this same attitude like, mining? Really? Do people mine things anymore? How relevant is that? Do they? Sure we do. And we are more relevant today than as an industry than we have ever been, and mining has been relevant to human development as long as there's been human history. We measure human history in terms of what? Let's see, we had the Stone Age, and what we were doing, we were picking up stones and making tools out of them. We ended up figuring out how to get metal out of the rock. We got into the Bronze Age. We had a supply shortage with a metal called tin, and so we quickly turned around. It took us about 1,000 years. Quickly turned around and became Iron Age technology, which led us eventually into the Industrial Revolution, where we started making machines out of all of this stuff. And all of the eras of human history, when you look at it from an anthropology or an archaeology point of view, talk basically about what are we digging out of the ground. And today we're still digging that same stuff out of the ground, and it's still relevant, although we talk about now as the computer age. 34 different mined materials, 34 different materials have to be mined in order to make a computer. 34 different elements have to be mined. So we can't have a computer age unless somebody is out there digging holes in the ground. But it's not just the computers. Here's what I want you to keep in mind as we talk. All of the things in your life, all of the things, not people, I mean things. Tables, chairs, floors, buildings, light bulbs, computers, iPhones, windows, plumbing, everything. All of those things are made out of stuff, right? And that stuff that they're made of, like steel or plastic or whatever, is made from a raw material of some kind. You have to have raw materials to make the stuff, to make the things. Raw materials come from two sources. You either grow it or you mine it. It's either grown, agriculture, and I'll include in agriculture growing trees, silviculture we call that, tree farming, so that we can make paper and things like that. Or we grow cotton so that we can have shirts and all. But the majority of stuff in your life, the majority of the things in your life, started out as rock. And someone had to dig that out of the ground in order to make the stuff, to make the things that make our lives enjoyable. Because if you think that you don't need the things that are made out of the mined materials, spend a day without them. First of all, no chair to sit on, because steel legs, actually, which means you had to mine iron ore and metallurgical coal and limestone and a little bit of manganese and that stainless steel, so you also had to have chrome and nickel mined in there, plus the plastic that you're sitting on. One thing about plastics, the soft plastics like these bottles probably came from petroleum, which arguably someone had to dig a hole to get that out of the ground. The hard plastics tend to come from coal, because we make things out of coal in addition to just burning it to make the electricity so that we have lights. But no chairs to sit at, no tables to sit at, no floor, because the floor is made out of concrete, which is made out of cement, which you make out of limestone, and a material called bauxite, and old tires. And then also to make concrete, you need things like sand and gravel, and then to have a concrete floor that's not going to fall down, you have to have steel reinforcing rods in it. So we don't have buildings without that material. We don't have lights at all, because the light tubes are made out of glass, and that's made out of silica sand and a mineral called chromium. And we don't have any electricity for those lights anyway, because we need copper wires to bring the electricity in here. So somebody had to mine copper. And you can go on and on and on. And when you talk about every physical thing, the wall that's made out of gypsum, the steel supports, the glass in the windows, you look at it, it all came out of the ground somewhere. Someone had to dig that stuff out of the ground. And so if I say, mining's pretty relevant to our lives today, I'm not just being an egotist and trying to recruit people to my way of thinking about things. I'm asking you to think about it. When when you drive home tonight on a road made out of concrete and asphalt, comes out of the ground, in a car, made out of all kinds of things that come out of the ground, and you get home and you go in and you turn on the television set and you sit down on a chair that's got steel springs in it. You walk on a nylon carpet. You sleep in a bed that's got springs. We don't have any of those things without mine. So, now that I've got your attention, why did I become a mining engineer? Because it's fun. Yeah, it's important. It's relevant. We wouldn't have society without miners. But mainly because it's fun. So that's what I wanted to talk to you about today. Because if you're going to be looking at careers, one of the things I think you ought to be thinking about is it relevant? Is it important? Is it fun? Some of you have asked questions about how do I choose a major. And Brittany and I will talk about that later on in the evening here. But that's something to keep in mind. Find something you enjoy, find something you're passionate about, something that really turns your crank and makes you go, ooh, that's cool. And I found it. It's mine. Now, so how in the world did I get here to this point as a mining engineer? So, because you're all looking at career paths and figuring out how you might go somewhere. I started off at a place called the Colorado School of Mines back in Golden, Colorado. The Fairfield Midland Engineering School. Actually, they've got a real good reputation in certain fields. Not just mining, which is a good thing because I didn't start off in mining engineering. I was going to be a physicist. So all you people are thinking, I'm going to be a physicist. See, you wouldn't even do that. And I tried. I enjoy physics. Physics is fun. Physics is relevant. All of this stuff. It just wasn't for me. Because what I found is something else. Something that really turned my crank, got me going. Something that I could enjoy doing. And that field turned out to be mining. If someone had told me when I started at that school that I'd end up as a mining engineer coming out of it, I'd have told them they were crazy. I was going to be a physicist, or barring that, I'd be a petroleum engineer, because that runs in my family. Never had a mining person in my family, so I'm kind of a black sheep. So I got my degree out of there, and I went to work for a mining company, which is what most engineers do. That is, out of school as an engineer, you typically go into the workforce. Because in general, an engineering degree is your ticket into the workforce. A science degree in physics or chemistry or biology, geology, things like that, typically you're looking at graduate school. Just as something to keep in mind, because I know some people have asked some questions about grad school and why grad school and that kind of thing. If you really want to succeed in chemistry, biology, physics, biochemistry, those kinds of things, you really should be considering graduate school. In fact, you might be considering a doctoral program if you're interested in doing any kind of research. All of the researchers that you have come in here and talk to you have PhDs. That's right, so do I. But I didn't have to have a PhD to be a successful mining engineer. I had to have a PhD to be a successful college professor. More on that later. But the idea is I went into the workforce. And so I worked for one of the biggest mineral companies in the country at the time, the Atlantic Richfield Company. You might know it now as ARCO. And we were looking at some incredibly big projects and mining coal and turning it into gasoline, mining something called oil shale, which has nothing to do with what you hear nowadays about shale fracking. This is something entirely different. But there are 6 trillion barrels of that out there in reserves in western Colorado. And if anyone can never figure out how to get that out of the ground, we will never have to worry about the Middle East again. It happens to take more energy to get the oil out of the oil shale than it does the energy value of what you get out. But someone needs to figure that out. So I worked at that. Decided I wanted to do maybe something else, so I went back to grad school, got a master's degree. After my master's degree, I made a total switch and went from working for one of the biggest mineral producers in the country to a little 6-person outfit who did very small mining contracting. And I worked there for a while and learned about things, because that's what careers need to be about. You need to be learning about things as you go along. And after a few years, I left there and I went to work for a slightly larger company that was interested in exploration for minerals. Primarily, we were looking for uranium. This is one of the many uranium booms we've had in this country, when people decided that you needed lots of uranium because we're going to build all these reactors. And then 3 Mile Island came along, and we haven't built a reactor in this country since, and the price of uranium went in the tank, and so I was looking for a job again. And that's when I decided that I'd go back and get that PhD, because the PhD is necessary if you want to teach at a university, or anymore, if you want to teach at a community college. They're going to be looking for people with doctoral degrees. That's the reality out there. So if higher ed teaching is on your list, be thinking at least a master's, probably a PhD, to even be considered for the job. Especially if you're at a university, because universities are all about doing research. And the PhD is the degree that indicates that you're able to do research. So, what do I think is so fun about mining that I would devote all of my career in general to it, different parts, including the research that I've been doing for the last 30 years or so at the university? Well, let me show you something about why I think that. Which one is that? That's not the right one. Let's do this one. Now, one of the things, let me stop this and go back a little bit, bring this up to full screen, turn on the sound, because one of my fields of research is called blast movement. That is, I look at where the rocks go when we blow them up. It's important, but more important than that, is it looks like this.
We're going to fire the shots on the 5,000 level. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
That's what I get to study. By the way, all those shots were from Nevada. That was put together by some people out in eastern Nevada at the gold mines out in Elko and Eureka County out there, of shots that go off every day at 2 o'clock. You blow something up. It's basic rule. If you haven't blown up something by 2 o'clock, just set it off. No. I want to tell you that the blasting that you were witnessing there, which looks like semi-controlled chaos, is extremely precise in that you could see that the holes were going off at different times. Those were real time, by the way. That wasn't slowed down. So you could see the wave of holes going across, that things were being set off. In a modern mine, those holes are timed to the nearest millisecond, thousandth of a second. We control it with radio-controlled blasting caps that are all individually programmed. So we can say when this one goes off and that one goes off and that one goes off and so on. There's a device, and when we need to use this type of very precise blasting, that talks to each individual blasting cap. It's got a radio receiver in it. And so you program in what pattern you want to go, what series it goes, and you push the button and it goes off. This is what goes off. It's a little bitty thing, right? Okay? This is called a booster charge. Also, please note, inert. This is not real. I can drop this. I can't bring myself to drop this, but I can drop this because it is inert. Safety is ingrained. And in this is a blasting cap. If you see one of these things anywhere, leave it alone. Do not touch it. Do not pick it up. Do not do anything with it. Go tell someone with a bomb disposal unit that you found a blasting cap. Or tell a mining engineer. We know what to do. Stay away from it. Go tell the bomb disposal unit to find it, because inside this blasting cap, or this blasting cap, there's enough high explosive. It's kind of like C4, although it's different chemical composition. But there's enough power in there to blow off your hand. I know that for a fact because one of the miners working for me when I was working for that small contracting company managed to be careless and had a blasting cap in his hand like this, and he lost that. We had to call a helicopter to medevac him out. These things are dangerous, which means we have to have special training to handle it. This, by the way, also, if you'll notice, says inert, which means that the explosive's not in there. But it's attached to this long tube, and so, just like this thing, we put it in this. Now, this will blow your hand off. This will take out, about a 10-foot radius around here of everybody. Little charge sets off big charge. Now, is that enough to blow up the rock? Not a chance. So what we do is we put this guy down the hole on this 60-foot long cord. The blast holes that you saw in that picture, the ones we use in Nevada, typically about 30, 35 feet. We can go 60 feet, we can go 80 feet, we can go about as far as we want to go with this stuff. And we put this booster charge down at the bottom of the hole, and then we fill it up with fertilizer. ammonium nitrate fuel oil. Look at people refer to it as ANFO. And all it is ammonium nitrate, which is fertilizer, and you mix it with diesel fuel. You want to know who Timothy McVeigh is? The guy who blew up the Murrah building in Oklahoma City before you were born. He did it with a truckload of 55-gallon drums of fertilizer that he had added diesel fuel to. It's way cheap and it's way explosive. The trouble is, one of these won't cause it to detonate. One of these will. So I use this to detonate the entire hole full of explosives. And I get those booms. Got some other things over here that we can talk about when we get into question and answer and everything. But these explosives come in all kinds of different sizes and all. Because as a mining engineer, what we're interested in is how are we breaking that rock up? Not just are we breaking it up and are we making a big boom and it's wonderful and fun and all this. But are we being efficient? Are we doing it right? How far does the rock move when we blast it? That gets to be important because what we're trying to do is get the valuable rock, which we call ore, separate from the waste rock. And they may be right together. And so if we take samples before the blast, we can say, okay, on this side of the line, this is the good stuff, this is what we want to process and get the gold out of. This is the waste, we want to throw that over the dump. And the chaos of a blast does this. It mixes the rock up. Well, we've devised ways of predicting where those individual rock particles are going to end up after those kinds of blasts. So that we're not taking the valuable material and throwing away because we think that's waste, and we're not taking the waste material and running it through the processing plant and wasting our money doing the processing because it doesn't contain any valuable stuff. We've been doing that kind of research over at the Mackey School of Earth Science and Engineering, where the mining engineering department is located, for the last 20 years. And we've developed some pretty good models. And we have helped the mining industry with problems like this. Because that's the kind of research we do. We do what's called applied research. We're trying to take basic science as we understand it. And so a mining engineer has to study a lot of basic science. We're trying to take that basic science and apply it to something. The mathematical model of what happens when that explosive column goes off is fairly complex. This isn't something that you sat down and just kind of drew some lines and a couple of equations and said, oh, it went over here. There's a lot of mathematical modeling going into this. But then we have to go out and say, we have to do what we call justify our model, or verify or validate our model. So we have a model that says, if you have a blast like that, this is where the material's going to go. But then we get to go out and look at before and after the blast and see where the material went. Now that's kind of non-trivial too, because there might be 50, 100, there could be a couple of 100,000 tons in one of those blasts. And trying to validate a model on where everything went gets to be a challenge. And that's the challenge of the research that we do in mining engineering. That's one of the fields that we do it in. One of the other things, what you got, see this? You want to play with that one? Don't drop it. One of the other things that I've been doing research in lately is in addition to being able to blasting things and blowing things up, we get to, in the mining industry, play with the biggest Tonka toys around. Tonka toys that look like that. If that's not a distorted picture. I mean, we didn't use focal length to exaggerate this stuff. He's actually about this tall on that shovel. That's made by a company called P&H, which was P&H Joy. We've got some other pictures here. Caterpillar makes a lot of gear. I've done a lot of stuff working with Caterpillar. This is I can't tell what size that is. But looking at it, I would say that's probably a truck that hauls about 300 tons of rock. So it's a 300-ton truck. Do you think it's a 93? It's what? So about 340 tons. All right, your pickup truck, standard pickup truck, half-ton truck, that means it hauls a half a ton. A 340-ton truck means it hauls 780 times more than a pickup truck hauls. The tires on this thing are between 15 and 20 feet high. It's like driving a 3-story house. There's the operator right up there. Notice he's sitting on the wrong side. Right? No, he's on the right side. He should be sitting on the wrong side. More about that later. All right, this 340-ton truck, if that's what we've got here, is being loaded by this shovel, and we try and size the shovels and the trucks together so that it loads it in 4 to 5 scoops. So if I were going to load that 340-ton truck in 4 scoops, that would be about 85 tons. Yeah, about 85 tons in each scoop. That's how big the shovel is. That's a slightly different configuration on a cat. That's just a big backhoe. You can see the backhoe. There's what I mean by the size of the tires. That's a 6-foot guy, so this is going to be about a 15-foot high tire. A truck like this costs, let's say roughly $1 million. That's without the tires. The tires are extra. And the tires cost about $50,000 a piece. There's 6 of them. And they've got a life of about 4,000 working hours. Well, if you're talking 24 hours a day, well, let's make easy numbers. 1 shift of 8 hours for 250 days a year. So that'd be 5 days a week, 50 weeks. That's 2,000 hours. Therefore, if you're running 2 shifts, you put 4,000 hours on that set of tires in a year. If you're running 3 shifts, 7 days a week, drop it down even further than that, and to change it out is 50,000 times 6. Now, why am I showing those numbers to you? Let's see what else I've got. There's that Cat 997. This is the biggest machine that Caterpillar makes. This hauls 400 tons. We've got a few of those in this. This is a humongous mining shovel that I'll come back to. So why am I talking about that? When I want to talk about research. The other research that I've been doing lately involves modeling, mathematical modeling of haulage fleets. Now, a haulage fleet is, I've got that shovel out there that probably cost me $5 million, and it can load a truck in 2 minutes. But if I only have one truck, by the time he gets back, the shovel's just sat there not done anything with all that money sitting there not doing anything. So what I do is I've got to put enough trucks in front of that shovel so that when one pulls away, another one pulls in, and he can keep loading. Or she. By the way, the best truck drivers are women. I just saw the study again last week. They keep doing the study because the men don't believe it. Women are safer, they're easier on the equipment, they're easier on those tires. But the idea is, companies get very interested in, I have enough trucks there to keep that shovel busy, but I don't want to have too many. Now, if a truck's going to cost me $1 million and it's going to be sitting there waiting in line. So one of the things that we've been doing with my research group is simulating, doing mathematical simulation of the haulage fleet. That is, we look at where the truck goes. The truck goes from the shovel and it goes to a place he's going to dump. Now, that could be a process where he's dumping the ore. It could be a waste dump. It could be as close as 500 to 1,000 feet. It could be as far away as 10 miles. It could be a nice short level haul. He might have to come out of a pit that's 1,000 feet deep of a 10% grade. And loaded, that means he's going to be making a maximum speed, the truck's going to be making a maximum speed of about 8 to 10 miles an hour. What's that? At 150 gallons of fuel per hour. So the mining companies get very interested in that, and so they have hired my research group to analyze how they're loading their trucks and where they're assigning the trucks to. And if you're in a big mine, you might have, a half a dozen of those big shovels out there. 30 trucks, and you've got a dispatch system that someone is sitting there when a truck finishes dumping, you tell him to go to a different shovel, so he's not just going to the same place all day long. And you got to balance that out so that you're getting the maximum efficiency. That's what engineering's research is all about, getting efficiency out of projects. We want to get efficiency out of our blasting, we want to get efficiency out of our haulage, and I just put this guy out there because it's pretty. That's a drag line at Peabody's Homestead mine. There's a car. That boom that the drag bucket is hanging on is about 300 feet long. So it's as long as a football field. And the bucket, if I remember on that particular device, is about 75 cubic yards. So if that back is 3 yards up, and I go 3 yards that way, and 6 yards, no, I got the wrong number, no, 5 yards that way, so 30 feet that way, 15 feet that way, 15 feet that way, that's the size of that bucket. The biggest one that was ever made, by the way, holds 220 cubic yards. I saw a picture of it one time with 4 Greyhound buses parked there. Big Tonka toys that we play with. Okay, so that's kind of what I do. Brittany asked me to come in and talk about the research I'm involved in. There are other research fields in mining. We are very interested in such things as Are the rocks going to fall down on our heads? That's a very important thing to be worried about. And so we have people who study that, and that field is called rock mechanics, or geotechnics. Rock mechanics. So if I'm driving an underground opening, I'm worried about, is it going to be stable? If I'm making a big open pit, I'm wondering about, are the slopes going to fail and come down? We just had a humongous slope failure last year at the country's largest copper mine, Bingham Canyon in Utah. If you've ever flown into Salt Lake, you look off to the south, you can see where there used to be a mountain, and now there's this hole in the ground that's 1,500 feet deep. 140 million tons of slide came down to the bottom. But because of the research that the mining engineering community had done and developed a monitoring system that was used in that, the mine knew it was going to happen and there were no injuries. They ended up leaving some equipment in the bottom that they're still digging out, but no injuries because of the monitoring of the slide, and they could see tiny movements in it developing over the years. The kind of device they use to monitor that is very similar to this thing, which is an electronic distance meter, which means it can look at a target up to a mile away and determine the distance from here to there to within 1/100th of a foot. Now the really cool, this is one I teach my students how to use for surveying. The really cool ones are robots, in that you set up targets all over a wall in a pit that you're interested in, and the machine sits there and it bing, 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 goes around, hits them in order, and it keeps track of any kind of movement. By using a device like this, the people at the Bingham Canyon mine knew the slide was coming. They could see it months in advance. Now the problem is there was nothing they could do about it. How do you stop 140 million tons of rock from coming? So what they did was they protected their people. And they made sure that when the thing finally let loose, and it let loose within days of when they thought it would, that they had everyone out of the path of that slide going down. How much time we got?
You got about 15 minutes left.
Okay. That's about what I was hoping for. So that's some of the other research we do. A final area that we do over in our mining engineering department, and by the way, there are only 13 of us in the entire country. We're not appreciated. But that means it's a small community, so the researchers all know what everybody else is doing. Is that we do a lot of work in research on ventilation of underground openings. If you're going to go underground, you got to have fresh air. And when we mine underground nowadays, it's not somebody out there swinging a pick. I mean, you saw the size of the equipment we're using in the surface mines. First time I took my wife underground at a mine was down in Death Valley, and this was back 30 years ago or so. And we were down a shaft in it's called a cage, it's an elevator. And we got off and she was all prepared to be claustrophobic because we're going in this underground mine. Walk out, the tunnels were 15 feet wide, 10 feet high, and at the intersections they had stoplights, red, green, yellow, for traffic control. The other thing was it was a bauxite mine, so everything was white, so everything looked just gorgeous out here. What's that? You got some pictures of that? See what you can pull up for underground while but One of the things we do underground nowadays is that we use a lot of diesel-powered equipment. Because we've running not 300-ton capacity trucks, but we might run 30-ton capacity trucks. That's as big as you're going to see around a construction site here. They're fairly low profile, that is, they can get through that 15-foot opening, but they still have to have all that horsepower on board and a diesel engine, and it spews out some nasty things that we scrub out of the air, but we still need to make sure that we're getting fresh air into the mine. That's the field of ventilation. And another thing that we need to worry about in ventilation, one of the things that happens in the mines in Nevada is they tend to be hot. And by that I mean, when we first went in the nickel mine out north of Elko, north of Carlin, the rock face temperature after a blast was over 100 degrees. Well, that's going to mean that the air temperature is going to be approaching that, and that's not a very pleasant place to be working. Plus you put a diesel engine in there, that's going to add some more heat. So ventilation, refrigeration, all of those things are important. And we've got one of the world's best ventilation engineers, Charles Cussage. We stole him from a research institution up in Canada, judging down to Reno. Didn't know what he was looking into. And he's now working with the mines in Nevada to make their ventilation more efficient. Make sure the miners' environment is what it needs to be, that it is clean, that it's temperature controlled, and that we're doing it in an efficient manner that saves money, because the last thing I want to leave you with about mining is mining's a business. We dig ore out of the ground because people pay us to dig ore out of the ground because they want the raw material so they can make the stuff so that we can have things in our life. If we can't do that at a profit, we don't get to stay in business, which means that I don't get to have fun. Because people won't pay me to have fun. They'll pay me to make their businesses more profitable. So that's the other thing about applied engineering research. We work very closely with the business community in order to make things more efficient. What did you find, guys?
That's a picture of a miner Lucky Friday running one of these drills. Those headings are about 8 to 9 feet wide. And heading or drift is horizontal tunnel underground.
Okay, the Lucky Friday mine is in the Coeur d'Alene area of Idaho, a place called the Silver Valley. It used to be the center of silver mining in this country. Probably still is the center of silver mining in this country.
That's well over a mile underground.
Now, straight down a mile. This is the head frame. That's the that has the elevator that you ride down. When we were there, we were on the 4,900 level. That's 4,900 feet below where the head frame is. And that mine, they're deepening to 8,900 feet.
That's what the gauge is like.
It's pretty rickety to me, guys. You sure we wrote on this?
I think that's the old. That's
That's the
the
old.
second iteration.
Yeah.
This mine's well over 100 years old. So.
Now, the reason we've got these pictures is because this winter, I took my seniors, including these two guys, out for a tour of mines. And we went to Idaho and saw silver mines there. We went to Montana, saw underground platinum mine. We went to Wyoming and saw a big surface coal mine. We went to Colorado, saw a big, huge underground molybdenum mine. And then in Colorado, we also saw what the country's largest underground coal mine.
This is those buckets, Dr. Ted was talking about. And then there's one with eight in front of We slip out 6'5".
6'4" and change. I think that's a 34.
130.
No.
They're 134.
Were they? Okay. Big drag line buckets. That, by the way, is the biggest surface coal mine in the country. It may be the biggest surface coal mine in North America, maybe in the entire Western Hemisphere. And so we're about running out of time. You got anything else we want to show them?
Danny,
Let's not talk about sunshine.
why
Yeah,
don't you see if they have any questions?
good idea. I've been doing all the talking. Oh, there's a mine up there called Sunshine. It's infamous because it was the site of the worst hard rock mine disaster in the country's history. 92? 91 people killed in a mine fire. Happened in 1967, 68, 72. 178 miners underground, 85 made it out.
Actually, one of the tour guides we had for Sunshine, her uncle was one of the 2 people that made it out. Very smart.
What that mine disaster did was it caused a wake-up call in safety standards for the mining industry. The safety standards since Sunshine have been so much more strict, most especially with what most of the miners died of in there was suffocation. It wasn't that they were caught in a blast, they were caught in a fire. And it's not that they were burned, it's that inhaling carbon monoxide kills them. And so now, every miner that goes underground, anyone who goes underground, miner or visitor or whatever, carries with them what's called a self-rescuer, which is a device that's a catalytic converter, and it will convert carbon monoxide to carbon dioxide for an hour. The idea being, if you've got an hour, you can get out. And no one has been allowed to go underground without one of those things since the fire. So it changed safety in the world. So Sunshine, kind of a sacred place. The mine has been reopened, by the way. Sort of. Any other questions? Yes?
Is there a certain like a focused area that you would consider explosive experts?
Yeah. Mining engineers in general. No, we, for explosive expertise. That is one of the areas of research that people get involved in. And there are a number of ways of looking at it. You can look at it from the chemical composition of explosives and things like that. Or you can look at it in terms of what I was talking about, of the use of those explosives. But there's a lot of research that goes into that because explosives are expensive, even if we're only using fertilizer to do this stuff. If you've got to move a lot of rock, you use a lot of explosives, so we're always interested in the efficient way of doing that. So there's lots of research going on in that field. In fact, there is a master's program at the Missouri University of Science and Technology specifically in explosives. So that is a recognized field, a recognized discipline within the field of mining engineering. And of course, there's all kinds of other uses of explosives, like killing people. So that's why the military sends people to the explosives master's program. Other questions? Yes.
So in your career, how many mines have you worked?
It's a hard question to answer, in that if you're talking about my career as a mining engineer, There's probably a couple of dozen because of what I was doing, which was doing contracting jobs. So we'd go from, we might have several mining operations going on at the same time. And as one of the managers of the company, I'd be providing engineering services for all that. Now, in my academic career, there's probably even more because when we do research, it's not a laboratory exercise. We go out to the mines to take the data because we're trying to apply our findings. And so right now I have 4 mines under contract that we're doing the haulage simulation in. And I put graduate students out there to take the data, and I go out to supervise the graduate students, and then we build the model, we do the report, we go back, we validate everything to make sure it's working, and then we say, would you give us some more money? So I can keep another graduate student alive. And so I have been able to work at a large number of mines in my academic year, even though I'm not technically an employee of those mines. But we've been doing work at those mines. I've worked at mines I've worked in mines in one capacity or another, everywhere from Mexico to Alaska. I've designed mines. I've designed a couple of operations that were to go into West Africa. Mining's an international activity. Because of my being in this field, I've been on every continent except Antarctica in mining-related things. Mainly hanging out with PhDs to go to places like Great Britain for our mining games. And I'll get them to talk about the mining games later on.
Since you brought some of your students, if you guys have any questions for them, by all means ask them, and maybe you guys want to talk about why you got into the field.
We both grew up in Elko.
Yeah.
Need to yell.
2 ways, fresh out of high school, you got 2 ways of making money out of high school. Working at the mines or working meal and fire crew, and you can tell which one gave us the job. My brother's getting a degree in forestry, so yeah.
It was one of those things growing up in Elko, you're around mining. There's Barron and Newmont right there, and they give back so much to the community there that just kind of seemed like a natural step. Also, I've been looking at all kinds of engineering, and mining really jumped out at me just because we're kind of a jack of all trades, master of none. Dr. Taylor had mentioned it. We take all sorts of classes. We take electrical engineering, mechanical engineering, environmental engineering, geological, civil, you name it, we have to take it. We're one of the only engineering disciplines on campus that has to take one of everything. And that really spoke to me.
That and working underground.
And both of those things spoke to me when I was that age. The idea that mining engineering, you'd think this is this narrowly defined thing. But it's not, because what engineers do is they solve problems. And the problems we have on digging those holes in the ground involve slope stability, it involves structures, so you got to know civil engineering, it obviously involves machines, so you need to know mechanical engineering. That machine runs on electricity, so you have to know electrical engineering. You have to have all of this background before you can even get to your mining classes. And some of my students find that rather discouraging. And then they get to the mining classes, and that's really discouraging.
You have to get over the hump of getting through your statics, your dynamics, and your fluids, and all these base engineering courses until you can start getting into ventilation and surface mine design and blasting, and rock excavation, and rock mechanics. You have to get over the basic engineering stuff in order to get to the actual mining stuff, which is awesome.
See, you don't have to take my word for it.
And we could go on a lot of field trips compared to all the other majors because I think we're at our biggest time right now, graduating 15 students next year. And the mechanical department's graduating 60. Yeah, they're in a slump and they're graduating 60. But because we're so small, Jay and I and all the rest of the mining students get to go on more field trips and whatnot than the other departments, which is really cool.
So when you think about 60 kids graduating, how many professors do we have working in the department per student? We've got, I think, 100 Mackey undergrads. That ratio, that student-to-teacher ratio is much better. I mean, we know all of our professors on a first-name basis. We know all of our lab assistants on a first-name basis. I can guarantee you, if you go into any other engineering discipline, by their sophomore year, they still won't have any idea. We do. We know all of our professors. We know all of our lab instructors. We know all of our lab assistants. We know everyone in the department pretty much. We know by our sophomore year because it's so small, it's so connected. Like I was saying with the sunshine thing, our tour guide for Uncle, one of the 2 survivors. This mining is so small, so interconnected that it's really amazing.
The head safety guy for the company I work for, two of his brothers died in a fire, but he told me that the week before we went. Just kind of tells you how small this industry really is. So, we could show them the Bergman shot at the bottle. Close it off.
Sure, go ahead and throw that one out.
Blasting underground
It's on,
is completely different from blasting on the surface. Just because to blast, you need to, what happens when the explosives go off? That's the start of an underground portal. We saw the orange flashes right before the big. That's this deck cord. Basically, you tie it off. It's a big, or tied into the round. This sets it off. This is basically filled with an explosive like C4. You tie it into this, and then that delay between this going off and the explosives was what these do. And if you don't time it perfectly, you'll freeze up the shot, so you'll waste all that explosives and break a tiny amount of rock. So the reason why Jay and I like underground a lot more is because it's a lot more technical than surface. Because you have so many more variables you have to deal with.
yeah, the thing on an underground blast is that you want to make sure that you're only breaking the rock in the opening you're trying to create. You don't want to be breaking the rock out into what's going to be your walls. So your perimeter shots have to be timed very precisely.
And these are timed at anywhere from 8 to 400 milliseconds. And that's how precise the miners can do it. And as mining engineers, we design stuff like this. So.
Anyone else got questions? Yes?
What's your average salary?
More than your average.
I would say that this year's crop is going to have starting salaries of, say, $65,000 a year to start. Now, for reference on that, your average civil engineer is probably going to have a starting salary this year of about $50,000. Now, does that mean that mining engineers are smarter than civil engineers?
Yeah.
Does it mean that the mining curriculum's harder? No, they had to take advanced thermo. But the idea is this. Here's Dr. Dan's secret for making a lot of money. People will not pay you a lot of money for showing up and looking pretty. I'm sorry. I knew that that's what you really had in mind. I hate to break your bubble. Britney Spears didn't show up at class today, right? So there are some exceptions. What people will pay you money for is to solve problems. The harder the problem, the more you'll get paid. Example, if the problem is how many burgers can I put on this griddle? Burger, 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 burger. That many. And what do I get paid for solving that problem? Minimum wage. Solve some of the problems we've been talking about today. Solve this problem. Solve this problem. I told you that all of the things in our lives are made out of raw material, and raw material has to come from somewhere. Everyone in this country uses, on average, about 40 tons of mined material every year. You were there when they brought the 40 tons. It happens in January here. Put it on the law. What I mean is, if you take all the mined material that we consumed as a nation, divide it by 350 million of us, it comes out to about 40 tons. It's been that much for quite a while. So we've got to be making that much rock. We've got to be mining that much material just so we can keep our standard of living. Now, let's add to the problem. How many people are in China? How about 1.3 billion, close order? In other words, if you took the population of the United States away from China, there'd still be 1 billion people. There's 1 billion people in India. Now, these are what we're calling developing economies, and the only way you can develop an economy, the only way you take it from poor standard of living to our standard of living, is you've got to use those 40 tons per person per year. Because that's where the things come from. That's where the schools come from, the hospitals come from, the roads come from, the power lines come from, the hospital equipment, the hot and cold running water, the sewage treatment. All of that stuff takes things that are made out of raw materials that go from the earth. How do we, in the 21st century, supply the needs of China and India, let alone us, and do 40 tons per person per year for every one of them, for 2 billion people? And I'm not even talking about the people who are below the poverty line. I'm not talking about that other 3 billion people on the planet who are living dirt poor, and the only way to get them out of poverty is to provide them with electrical power and clean water and sewage treatment plants and schools and hospitals and lights and roads, chairs to sit in, books to read, computers to use. All of that takes money. The problem that faces this planet, that is, in my opinion, greater than global warming, is how do we provide those raw materials to 7 billion people on this planet without screwing it up? It would be tough enough if we allowed ourselves to just ignore the environment. Well, we can't do that. They know we can't do that. We teach environmental concern and the fact that you have to follow the environmental rules in order to have that mine that's going to make money that we're going to have fun in. But we've got to do that not just here in Nevada, not just in the United States. We've got to do it across the world. That's a problem that people will pay you to solve.